right, good morning. The exam has been posted and will be available to you on Blackboard at 12:30. You have until Tuesday. Bring it in the same kind of, pretty much the same format as the last exam. And then here's the way the course is going to work from here on out. You're just going to have 3 labs and a presentation that are remaining. The way the labs are going to work are your groups. You're going to go through the topical guide objectives and you're going to type that up. That's going to be the first part of your lab report. I'm going to post what I expect from each lab report and what I expect from you for each week. So to let you know the things you're going to download. You're going to download Electric VLSI Designer and WinSpice. And these are freeware. WinSpice, you have access to the all of its features for 30 days. You only need it for 28. So
you get 2 extra days.
You get 2 extra days. Do whatever you want. All right. Matthew McConaughey there. So, but basically, the objective of these labs, it's not supposed to be terribly complicated. What you're supposed to do is get familiar with the tool. You're going to be building from circuit level designs. You're going to build a cell. You're going to build and then you're going to kind of do some gate level simulation. You're going to use that to actually build SPICE files, which we're going to be learning about today. And eventually you're going to take some Verilog code, make some minor edits, and then you're going to go in there and you're actually going to synthesize a multi-cycle MIPS processor. So by the end of the labs, you're actually going to have a chip made. So that way you could theoretically, you could take it to Foundry and actually have your own chip. So you'll be able to see it in the layout, you'll be able to put it in the pad frame, you'll be able to do extraction, you'll be able to do tape out, you're going to learn all of these things. And then you'll be able to go through and make, do a little check off of all these. The objective is to kind of get you familiar with the tool, and you can say that I have experience with all of this, so that way when you apply for jobs, you have a breadth of experience on these. It's not meant to be terribly difficult or too terribly time consuming. So in order to do that, we need to learn about circuit simulation and tools and what this actually is. So fabricating chips can be time consuming, so we're going to be using a lot of something called electronic design automation and simulating tools. There are 4 major types of simulating tools. Process simulators predict how factors such as, there we go, okay. We kind of learned about all this process variations, time, temperature, voltage, how that affects all the physical and electrical characteristics. We're going to be looking at an example of something called a process file that actually defines the process, all the lower level quantum aspects of it, all the way up to your initial threshold voltage, your gamma, your electron mobilities for PMOS and NMOS, and how you can use that to actually simulate a circuit. Circuit simulators are device models and circuit netlists, so we're going to be learning about circuit netlists today, to predict circuit voltages and currents which indicate performance and power consumption. Logic simulators, you guys have done a lot of this already, widely used to verify correct logical operation of designs in a hardware description language. What are a couple of examples of 8 hardware description languages?
VHDL.
What's another one? Verilog. There you go. You guys have learned a couple of good ones. So, architecture. See, you guys have actually learned something at the University of Mississippi, despite all odds, despite our IHL. And architecture simulators, sometimes offered with a processor's development toolkit, works at the level of instructions and registers to predict throughput and memory access patterns. So remember Amdahl's law back from 385. You want to be using actual architecture simulators. You put all these registers together. You're doing either parallelism or a single cycle or multi-cycle, and you can use these to test your throughput, to test your efficiency, your reliability. You can use it to test power consumption. So all of these are used to generally figure out how your chip is going to be working at different levels. The one that we're going to be learning about mostly in this class, we've learned about Verilog already. We're also going to be learning about this tool called SPICE. SPICE stands for Simulation Program with Integrated Circuit Emphasis. Solves nonlinear differential equations describing the components such as transistors, resistors, capacitors, and voltage sources. So RC delay models, SPICE does that. Capacitance and voltage sources, SPICE does that. You put these in there, you do your transistor sizes, you base it off of the technology file, and you can actually figure out how your circuit is going to actually work based on simulation waveforms. Now, I'll refer to it as a SPICE deck. The reason why it's called a SPICE deck is because it was originally written in Fortran and was written for punch cards. So you get a giant deck of punch cards to try to simulate your file, right? So for those of you who are not familiar, that is what a punch. And does anybody here not know what a punch card looks like? Or actually ever had one? If you ever get your opportunity to get your hands on one, I highly recommend it. It's good nostalgia, and you won't drive the older folk crazy. What do you mean punch card? Neck ring. Same thing when you guys are 60. What do you mean smartphones before they implanted them in your brain? So the first thing we're going to do is we're going to build a simple SPICE deck for this circuit. We have input voltage, which we're going to learn how to write voltage sources. We have a 2 kilo ohm resistor. We have a 100 femtofarad capacitor, and we have our output. So this is what a SPICE deck looks like, and what we're going to be doing next is we're actually going to be going into detail as to what each of these means and how you would actually use this to draw up a SPICE deck for the future, so that way you understand what's going on. All right, so first things first, SPICE netlists are case insensitive, and don't worry about Facebook. Comments are denoted by a star on the beginning of the line. Every comment line must start with a star. It's not like in C where you can go like backslash star and then everything up until star backslash, right? You have to have a comment on every line or else you're going to get compiler errors. So a good, if you're going to have a quality header file, what you want to do is first thing you want to do is have the file name written. You want to say who wrote it. So when you guys do this, you're going to put your names here. You want to write your email. When you get into industry, let's say somebody in a different part of your company is using your code for reference and they can't figure something out. They can sit there and bash their heads for hours trying to read code they didn't write, they didn't understand, or they can email you and ask, and you go, oh, this is what I did. They go, oh, and then they properly use your code. And so you want to also write the day you created it and the last update. You'll see in future examples, I'll say I'll have like March 23, 15, so you can track your updates. So that way you know precisely when and where you did something. So let's say you chose a different, you scrapped this file, you developed a new one, you have a different date, but then you're trying to figure out why this code's not working. You go in and you realize you have your old version of your file compiling instead of your new one. Saves you trouble. So this is, you're going to want to do this. When you write code, follow this. This is a very good fundamental. And do this for pretty much, I would recommend doing this for any code, regardless of just this class or in the future, because then the more comments you have, the more you understand your code, the better it is to follow the design process. So next, we're going to talk about this thing called a dot option post statement. It instructs SPICE to write the results to a file for use with a waveform viewer. The final statement at the end of the SPICE deck must be .end. So what you're going to do, you're going to write some code. If you write .option.post, the first thing you do before you write any other code is just write .end. And you're going to put everything else in between. But if you don't write .end, it won't compile and it'll drive you mad. So every time I write a SPICE file, .option post, .end, and everything else goes in between. So as I've indicated, also you want to name your node. So ground, you're going to name GND because that's inherent to SPICE. It's a reserved character. I also call this out and in. And so what's going to happen is your resistor is in and out, but your voltage source will have your positive tied to ground, and your positive is going to be tied to node N, and your negative is going to be tied to ground. And the reason why this is important is because SPICE decks to maintain consistency, you have to have your nodes labeled correctly. So first things first, we're going to describe what a voltage source actually is in SPICE. You're going to have your node name, the plus node for the voltage source, and the minus node. So here this is going to be Vn, and we have in and ground. And we're going to discuss type of input signal. It can either be pulse or piecewise linear. We're going to talk about that in a minute. And then based on that, you're going to have the timing requirements of that input signal. So I talked about the piecewise linear means that you're just going to be writing precisely what you want the waveform to do and nothing else. Pulse means you're going to have it cycle. And then if you're at the bottom, you're going to do a dot tran, which is we're going to be using this to actually generate over a certain amount of time. So if you want to simulate for a certain amount of time, and the pulse can happen like 12 times, your output waveforms and your output files will actually have data for 12 cycles. Whereas for piecewise linear, if you have just one, you just have one raise, but then you have like 800 nanoseconds, and you still have 700 nanoseconds, it'll just remain that last value, the remaining 700 nanoseconds. So this is why differentiating between piecewise linear and pulse is important. Piecewise linear denoted PWL, so in your code here, you would have VN, N, GND, and then PWL for a piecewise linear. That describes the exact times and voltage values from the voltage source only. The each input is the time. So let's say initially you're going to have 0 picoseconds, and then the voltage at that time. So you're going to have 0 picoseconds, and then 0 volts. And let's say you want to have a 100 picosecond delay, and then you're going to have a 10 picosecond transition to 1, right? So here's what this means. You would have 0 picoseconds, 0 volts. 100 picoseconds, 0 volts, because that gets us here. And then you're going to have 10 picoseconds, right? So that's going to be 110 picoseconds, and then 1.0 volts, right? So that is the time, then voltage, time, then voltage, time, then voltage. And then pulsed source, and in that code you're going to use pulse, describes a cyclic set of voltage values from the voltage source. The values of the pulse source are as follows. So what you're going to have is you're going to have pulse, so you'd have your Vn, in, and ground, right? And then you write pulse, and then V1 here. So let's say this is 0 and this is 1, right? So this would be 0, 1. TD is your initial delay time. TR is going to be your rise time. Tfall is your tfall. Pulse width is the length of time it's going to be between the rise time and the fall time. And then period is going to be the length of your period. Right? So that's how, and what's going to happen is that period will keep cycling. So let's say that your pulse width is 100 nanoseconds, and your initial delay is 10 nanoseconds. And so you would have a rise time and a fall time, and then you have this amount of time before your period starts again. You can just think of it, if you're recalling back from algebra, and you're talking about shifting on a function. So then you can think of this the same way. It's going to recycle that first 10 nanoseconds would be the first 10 nanoseconds of this, and so forth. So that cycle is going to, yes, 10.
Is there an assume time if you do not specify, so picoseconds or nanoseconds?
No, you have to specify.
So we'll throw an error?
Yeah, we'll throw an error. That's a very good question. Yes, if you do not state a time for pulse, you have to write all of these values out, or else it'll give you an error. And so I actually have a couple of examples here. So here we have, for this particular code we want to do, this is going to be in and ground. It's piecewise linear. So I actually kind of described what's going on here, except I've added an extra at 1 nanosecond. So it's going to be 0 picosecond, 0, 100 picosecond, 0, 150. So we have a 50-second rise time. And it's 1, and then it goes all the way out to 1 nanosecond where it'll end. Right? So if I wanted to have a, let's say I had a 100 megahertz cycle, right? So that's 100 times 10 to the 6. And so we actually need to know what we're going to use. So here, these are our micro times. So that's 100 times 10 to the 6 cycles. That means 1 over 100 times 10 to the 6 seconds per cycle. So that's going to be 100, 1 times 10 to the negative 8. Here we have 10 to the 6 and 10 to the 9. So if you want to have 100 mu s, right? That's your total cycle time. Then based on that, let's say you have your rise time is 1 microsecond, and your fall time is 1 microsecond, right? You're going to have 1 rise and 1 fall per cycle, right? So what you're going to do is then you'd have 100 minus 1, so that gives you 98. So you divide it by 2. That's going to be 48, right? So what you would do, if you want to do a pulse, you do pulse 0, 1, 1 mu, 1 mu s, 1 mu s, 1 mu s, 48 mu s, and then 100 mu s. And you would insert your delay here. So let's say you did 10 mu s. So I mean, what this line of code means is we have derived a 100 megahertz cycle with a delay of 10 microseconds, and we have 1 microsecond rise and fall time. And this will actually happen throughout this. So this is the way to do it, dividing it by 2. And I have an example problem here next that shows you how to do the another example of how to do this. So this one's a 1 gigahertz signal. Write a line of SPICE code for a pulsed input for the following: a circuit with a 1 volt supply that has a node Vin which receives a 1 gigahertz input signal. The rise and fall times are 1/20th of that total cycle time, and the initial delay is 100 picoseconds. So here I've calculated 1 times 10 to the 9 cycles. That's 1 times 10 to the negative 5. That's 1 nanosecond, 1 ns. TF equals 120 times 1 nanosecond, 50 picoseconds. So therefore, we also have defined TD as 100 picoseconds here. So therefore, we have our 1 times 10 to the 9 minus 50 picoseconds. Minus 50 picoseconds. This should be, actually this should be 400. Right? So we have 100 nanosecond delay, we have a rise time and fall time, and then we have, so the way it works, you're going to have, it's going to start here, it's 50, and then this value and this value, so 50, so this was out of, let's say this was out of 1,000, so that's going to be minus 100, which is the same thing, so that's going to be divided by 2, which is actually equal to 450, which is what I actually had it right. I doubted myself. So it's going to be 50, 450, 50, 450. So that's how that works. So then the final line of code, Vn, in, ground, pulse, 0 to 1, so that's our initial value, the final value for the voltage. We have a 100 picosecond delay. Our rise time and fall time are both 50 picoseconds. Our pulse width is 450, and then the total time is 1 nanosecond. So here, we're actually going to define the plus and minus of our resistor and capacitor. So it goes R and whatever denotation you do, so it can be plus node, minus node, and value. So here it would be R in out to K, and you always call it R1. I should note here that these variable names that you're using for resistors, you cannot use the same one more than once, or else it won't compile. So here you just call it C1. This one is out and ground, and it's 100 F. That's 100 femtofarads, and that is what our code is here. So if we go back to this original code statement, we see we have generated option.post, we have generated our voltage source, and we now have our resistor and capacitor. So next thing we're going to do is we're going to try to figure out what all this means. So that .tran is a command that tells us, I should let you guys see this. So femtos 10 to the 15th, that's 100 times 10 to the 15th femtofarads. Picos times 10 to the 12. 9 is nano. You should use, when you're, this is U, like we know that the symbol is mu when writing code, but use U in SPICE, and M is milli, K is kilo, etc. So the reason this is important, especially when you're dealing with nanotechnology, now we understand what that means, like 22 nanometers, therefore our lambda is going to be 11 nanometers, 22 nanometers is the size of the poly, and so on. So the .tran command we defined formally, it measures the response of a system to a change from equilibrium and indicates the step size and length of the plot. So step size here, that's line of code, we need to 20 picoseconds in 1 nanosecond. That means it's going to measure the value of the voltage. Here it's plotting V in and V out, so it's going to measure the input voltage and the output voltage every 20 picoseconds for 1 nanosecond. Does that make sense? That's what .tran means. .tran means every 20 picoseconds for 1 nanosecond, give me the measurements. And here, the next line, .plot, you're actually going to be plotting the input and output voltage. So all of what's going to happen is every 20 picoseconds, it's going to write the exact value of V in and V out to an output file. And then from there, you can use those values to do a waveform generation.
Is that the plot right there?
No. What this is a .lis file, which is kind of simulating the plot. So let me zoom in here. So it actually has the exact values. So you're actually going to have some sort of rise time here. And it's actually going to, so here it's going to, right? So what this is representing is this is your input voltage that you have wrote, and this is your RC delayed response that you're going to be measuring. So what you're actually going to see, so these are your values that are there. And then what's going to happen is you're going to have a waveform generator. HSPICE use A waves. You're going to be using electric VLSI designer to do this. You're actually going to generate a pretty font here. So here you have your initial delay, you have your 50 picosecond rise, and then you have the remainder of your time, right? Then you're going to have an RC delay response to the output. So what's happening here is you have written a .tran where it's measured at every 20 picoseconds for this 1 nanosecond, right? You've written this input voltage. you've designed the RC such that is properly configured and will properly compile and the circuit is together, and then this will be so here we have now written this segment of SPICE code. Have your input, write .post, first thing you do after .post is write .end. If it has a star, it's a comment. VIN, in ground, piecewise linear, at 0 picoseconds, it's 0 volts. At 100 picoseconds, it's 0 volts, so that simulates a 100 picosecond delay. At 150 picoseconds, it's 1 volt, so we have a 50 picosecond rise. And then at 1 nanosecond, it's at 1 volt still. Because the reason why we'd want to do something like this is because of an RC delay, you're going to have some sort of time. So we're trying to figure out how long that's going to go. We have variable name for R. If it starts with an R or a C, that R means a resistor. C is going to be a capacitor. What we're going to learn later is M is going to be starting for transistors. In and out 2 kilo ohms, and the capacitor out to ground is going to be 100 femtofarads. We do our transient analysis from every 20 picoseconds for 1 nanosecond. We plot V in and V out. And then I want you to know these variables. Now, what I was alluding to over here was R1 and C1. Each one starts with R, and then you can add anything else. But if it starts with R, the first value in the line is going to be a resistor. If it starts with C, it's going to be a capacitor. If it starts with L, it's going to be an inductor. So if you remember for your classes, all your LRC circuits, you can actually go back and actually plot them out and see how they actually work. Mutual inductors, K. Independent voltage source, which you're not really going to worry much about in this course, but it's good to know because, again, if you're trying to do electronic circuits, especially taking 360 over the summer, you can use your WinSpice to actually verify your results for your homework. M, MOSFET. You're going to be using that quite a bit here in this course. So we're going to learn how to implement that, and D for diode. So these are the, yes, Coleman.
Was that plot up there produced by WinSpice?
That plot is actually from the textbook, but the textbook is going to, there's different things. I can actually show you, let's see. I'll show you. I'll bring it in next class, but I can show you something from my dissertation, where I actually render them in HSpice. Okay. So, also you're going to be doing a number of plots in WinSpice that are pretty similar, and you guys will get familiar with that. But the difference is how it looks. By and large, it's mostly colors. How it's rendered in the colors. Okay, does anybody have any other questions on this before I move on? Yes, Terrence.
Does it label it for you? The labels were on there. Does it present the labels like that?
When you,
You mean like
oh, you mean on the graph?
Yeah.
Yeah, if you label it, what's going to happen is it's going to have some sort of. Give me a split second here, okay? I want to see Google here. Go. All right, so Arthur Morrison, that should bring up my dissertation. Yep. All right, so this is going to take a while to download because I'm insane. My dissertation was 285 pages long, I believe. But I have tons of simulation response in HSpice here that I can show you diagrams. And since we've covered, you guys, I will say as well as downloading, side note, I'm insanely proud of how well you guys have done this semester. I never thought we'd get as far as we have. It's actually been a challenge. It's a good challenge to have as a professor, trying to keep the material up so that way I can stay ahead of your progress. And it's like, oh man, I'm gonna be exhausted. I gotta take a Saturday lesson plan again. I think it's gonna take 2 weeks. You guys go through in a week. I'm like, but that's good. I mean, that means you guys are understanding it and getting through it well. So this is my dissertation and blah, blah, blah. And so, yep, lots and lots of figures. So here's an example of a H-Spice simulation. Let's see, let me find a better one. But what this one generally is this here. These are voltages. So this specific one, this is the design of the circuit I did. And here I have input signals and output signals. And this one is actually a power waveform. The red spikes are your typical NAND gate. And these little yellow spikes here are the circuit that I designed. So let's find better ones. It's going to go.
Some latex.
Part of it. Okay, so here we go. Here's some spice waveforms. So we're going to be learning about how to define certain values, right? And you're actually going to have so this is energy. I've defined it energy, time rise, time fall. Which you guys are going to learn how to do that today, actually. So you have some sort of rise time, and this is what's known as a Monte Carlo analysis, meaning I took the sizes and values of a transistor, and this is the delay with respect to the sizes. And this is the energy, and however, as I sized it, the average power consumption came down for this particular design. So this is V in, V out, kind of a small version of what you guys are doing. Let's see if I can find some more. That I know this chapter has nothing to do with spice. But that's VHDL. Look familiar?
This chapter.
I did. I really did. But and algorithm, and here's another H-Spice simulation for power consumption.
That looks messy.
Yeah, well, this is 256 different inputs. So that's known as an S box for those of you who are. See, and here's the algorithm I wrote and flow chart. And it's the next section. It's going to have the real. So. This is another one. Okay, so this is a really good description. So basically, you have your input, which is the first 3 lines are inputs, and then line 4 is the C output, which is important because that was the only one that's different from the input. And then this is instantaneous power consumption. So one of the contributions is for my dissertation was that if you hook up a circuit, like a smart card to an oscilloscope, you can actually use the instantaneous waveforms based on the spikes, which you guys now know enough to understand this. So if you design CMOS circuits in a certain way, you know how much the power consumption is going to go by if you know how the circuit works, you know that your PMOS transistors, if you get a 1 on a certain value, it's going to spike up higher than it would if it's a 0 versus, and specifically if you have a NOR gate, a 2-input NOR gate, you're going to get a 0 on the output if both PMOSs are set to 0, right? But if you have one or the other, it's going to have a different output power consumption because one of them is on and the other one is off, right? So you're going to get different power spikes, and you're trying to make it as consistent as possible. If you get a large enough circuit, you saw process variations, you saw voltage variations, right? So if you get power spikes that are large enough and you know how the circuit works, you actually are figuring out what the cryptographic key is. So the objective is so you can circumvent all of the software security by doing something known as the side channel check by figuring out these average power consumption. So I was trying to figure out how to make circuits that are consume consistent power. So I use dual rail pass transistor logic, which is A and A, creating an A and A bar input for every single input. And then you guys know what pass transistors are. And so, see more. See, very, very consistent is composed to your typical NAND gates, which you can.
Yeah, there's huge spikes.
Yeah, there's huge spikes, and you see how they're different heights too.
Is that just from 2 being used?
Yep, exactly right. Exactly right. And that's here we go. Now, okay, so now we're getting to the good stuff. Okay, so these are all SPICE waveforms, and you see how the power consumption is pretty much the same. And what I did was S-Box has 256 input possible combinations, so the power consumption is very similar. And then I grabbed 16 random input combinations and threw up the waveforms and said, you tell me what those inputs are. And they said, we can't, and that's when, so because you can't, you figured that out, you are now a PhD. So there you go, that's the miracle. So four years of work summed up. But anyway, so those are all H-SPICE. So that's all SPICE. So basically what I did is I designed my circuit, and then I actually put it in there and was able to do what you got, some of the things that you guys will be doing in this course. So this is just plot V in, V out, resistors. So DC analysis. So this is kind of what I did a lot of in my dissertation. So if you were looking for something that I was amused by myself, somebody actually on the Wikipedia page for clock rate, this was pointed out to me, somebody actually cited my dissertation on Wikipedia, which I thought was funny. I was like, I'm not sure that's the authority. Yeah, exactly. I was like, I'm not sure that, but I'll take it. Yep. So remember we had this drain source current from section 2. And so I presented this plot here where we had transient analysis by changing the beta sizes. We were able to get the same amount of voltage based on this. So basically what's going on here is we're going to be doing a specific type of transient analysis called a sweep, where we're going to set the gate source voltage to certain values and then do a transient analysis again. And based on that, we're going to get our specific delays. I'm going to show that here by just doing a simple NMOS circuit. So here, this is our NMOS circuit. We've set the width of 4 to 2. We have gate source and gate drain voltage, and we're actually going to be creating voltage sources based on this in order to actually properly do the transient analysis. So the first thing I want to cover here is something called dot include. So what's going to happen is there's an actual technology file here. It's called IBM_65nm.lib. Basically what that means, it's a library for the 65 nanometer, and this one was done specifically by IBM. When you do dot include, it's going to include the thing I'm going to show on the next screen, which is all of this, right? So you already know, you don't know all of these. You do know a few of them. You do know initial threshold voltage. You'd use this one to try to figure out body effect. You do know various capacitances.
Is that VSAT and a set?
Saturation voltage, yep.
7.5, is that 8 times 10?
Mm-hmm.
7.5 times 10.5.
Where is that?
That's first column. First column, yeah.
Oh, yeah, about halfway.
Keep going.
Keep going
There. Yeah.
E5. I'm not
The units for that.
not sure. Yeah, half of these things I don't. No, it's fine. But that's the point of me putting this up. Half of these things you're not going to know, right? Because you know gate source capacitance, gate base capacitance, gate drain capacitance, but a lot of this is kind of the real quantum level, and a lot of it is kind of determined specifically by Well, I'll admit I don't know why they have VSAT, where they have this specific, E times e to the 5 there. That's huge. I don't know what that means. So, but what you need to know is this specific notation here, where it says CMOS N, and then later down here where it says CMOS P. You're going to be using those to identify your MOSFETs in your SPICE file. Tox e to the negative 9. Look familiar? All right. So the reason why that's important is because when you write your code, you're actually going to be using CMOS and CMOS P. So you're going to be having M, I would call it N0. You're going to have drain, gate, source, and then you're going to write CMOS, and then there's going to be a number of things that we're going to cover here in a second. And M means it's a MOSFET. My naming notation is P and then a number, drain, gate, source, CMOS, P. So here, what we're going to do is we initialize our file here. The dot temperature value here, that's in Celsius. So 25 degrees in temperature is a common simulation because that's typically room temperature. So what happened is we had an NMOS transistor and we have gate, source, and drain, right? So this was tied to ground, this was tied to ground, and we had our voltage here. So we're going to initialize these two values, VGS, G, and ground. And we're going to say 0 for the time being, because what we're going to do in our transient analysis, we're actually going to change the value by using our .tran command. And then we're going to insert the transistor itself. Here is how we do it. So M name, remember I said M like N0, right? So that's what name means. Each of these have to be unique, and it has to start with M in order to put it in the circuit. And then you have your drain, gate, and source. So here, gate would be G, drain would be D, and then source is going to be ground, right? Body type, let's call it body underscore type. We'll say CMOS N, because it's an NMOS transistor, and we're using that specific technology file. If the technology file said NMOS, we would just write NMOS there. So if you put in the wrong one that doesn't match your technology file, you'll get a compiler error. Now I have these other. Now this plus, you're basically including your concatenating onto your line, your comment line. So it's plus means it's part of the previous line. So you're going to have your width and your length. And then we have these values called area source, area drain, perimeter source, and perimeter drain. These are not required. There are default values, but you can modify them if you like. So we can assume that if the width is properly sized with our technology size, then the area source is just width times 5 for isolated contact diffusion, shared contact diffusion, and merged contact diffusion. The values here that I have in this code that we've written, they're just the default values, and you could actually just leave that line of code off and it would compile just the same. But the things that you absolutely need to have are, drain, gate, source, body, and then type. So MNO would be our NMOS transistor, drain, gate, ground is the source, right? So then, and then the body is usually also tied to ground unless you want to do some sort of simulation with body biasing, which you won't really be doing in this course. So I think there's one group who did their essay on some sort of body biasing or was interested in doing it. But then we have our length and width here defined. And then these area source, area drain, perimeter source, and perimeter drain values. And I've already mentioned body biasing. All right, so the sweep command, so this is where everything comes in, right? So we're going to use a .dc for our transient analysis. That's where we're going to be where our .tran was. And what a sweep command is, it performs a transient analysis of a step function for each step of initial function. So what we're going to be doing is we're going to be going from 0 to 1 for VGS, so if we have our NMOS transistor here, So this is VGS, right? And then we have VDS. So we have some sort of VDS value, and we're sweeping. So for every instance, so we go from 0, and then we're going to go from 0.2, 0.4, and so forth. But for each instance of this, we're actually going to go from 0 to 1 in steps of 0.5. And that's how this works. You remember our graph starts VGS 0.2, 0.4, 0.6, 0.8, and 1, right? And each of these is 0.05 for drain source. So this is VGS versus VDS, right? And so this is how it actually steps. It steps 0, 0.5, 1, and puts those values in and sees how the transistor actually operates. And it goes all the way to 0.1 and then 0 and so forth. And it's going to write all of the results to the output based on this code that we write here, right? So we have our transistor, drain, gate, source, body, CMOS N, width and length. We have our DC analysis, our dot end, and then for just an NMOS transistor, this is how it would end up, right? We're measuring IDS, VDS for each. So this is, it's not going to go very high when VGS is 0.2, 0.4, it goes a little higher, 0.6, all the way up to 1. So you have some sort of transient response. And if you recall, remember our IDS equations? Beta, it's related to the drain source and the gate currents. VGT minus VDS over 2 squared. So that's where that comes from. So does anybody have any questions on this before we kind of show you how an inverter works? All right. So let's do a inverter. So I do the same thing. Now, we know that inverter is 2 to 1, right? For PMOS to NMOS. And we also have defined that the width, or the length, is equal to 2 lambda, right? So if the NMOS is 2 to 1 here, that means multiply each of these by 2. That's where you get 4 to 2. And then you multiply that by 2, so that's where we get 4 to 2 and 8 to 2. Which I think you guys already know, but that's just a refresher. So in order to do this, we want to have our supply voltage, and we're going to introduce this concept of a dot param. So then you can call your value supply equal to 1.0. So now you've designed your, your voltage there. So you can think of it as a variable in your function. We're going to be going, that's going to be another thing, dot global, which is going to be the same thing for, we're going to be designing subcircuits. So now we're going to build an inverter. And the next step is using those inverters to build like a fan out of 4 inverter with different sizes. And we can have an initialized size and then other values we're going to put in. But dot param is only for the highest level, whereas the dot global is going to be able to go into each subcircuit in your SPICE file. So we're also going to use this scale option that's going to allow us to set our lambda for our DSC. We're going to define formally the scale option as allowing us to indicate the width and length of a transistor with respect to a set value. Right? So now this allows us to tie our DRC, which I'm sure you guys remember this, right? We have our design rules check. All of those values in the in your technology file have to match the DRC. So that means where polysilicon's 2 lambda, and then when you lay out your chips, it's going to meet this. You may lay out your cells for your stick level diagrams and being able to make your polygons. You're going to combine your technology file with your C in order to actually properly simulate the circuit. So, like before, we're going to use our dot option, and we're going to call scale, and in this case, we're going to call this 45 nanometers. And then we can define the voltage as VDD. This is the name of it in the specific circuit. We have reserve values VDD and ground. This is acceptable, meaning that in your circuit, the specific VDD matches supply voltage to ground, so that's your plus and minus, and that's equal to supply, which we have defined earlier as 1.0 volts. And I've also made a note here, you must put any parameter in single quotes into the spice stack. So here, we are actually generating a pulse with our supply. So we have VN, we have A to ground. So here if we have an inverter, we have A, and then we're going to have a PMOS, and then an NMOS. And here it's 8 to 2, and this is 4 to 2, right? So when this is called, this means that the W and L, meaning 8 to 2 and 4 to 2, are related to supply, and it compiles as 4 times 45 nanometers, 2 times 45 nanometers, 8 times 45 nanometers. Or you could actually just put in 90 nanometers, 180 nanometers, 360 nanometers. Both are correct. But this allows you to, this will save you some time. Okay, so then let's recall Y is our output. So that's our, and then we have our source. Here for the PMOS, it's tied to VDD. For NMOS, it's tied to ground. And here, in this particular simulation, our body is also tied to VDD. If you recall the layout of the PMOS transistor from back in section 1. Some people also can put ground, and you can mess around with your spice and see how that improves your speed versus your ability to conduct in the circuit. And then your stimulus, you measure the transient result every 0.1 picoseconds for 80 picoseconds in this particular example. And here's our final spice code for this circuit. We have our 90 nanometer library option post. So first thing you do is .end. Room temperature, option scale is 45 nanometers. We have a supply voltage, VDD, which we have tied to actual VDD and ground as our nodes, right? See, there's the same nodes here. And then we have VN. VN is going into A and ground, our pulse from 0 to supply voltage. We have a delay of 50 picoseconds. We have rise and fall times of 0 picoseconds, pulse width of 100 picoseconds, and an overall time of 200 picoseconds. We have tied our NMOS and PMOS. You see I have MN0 and NP0, drain, gate, source, body, CMOS N, CMOS P, and our widths. I have included our area source, perimeter source, area drain, perimeter drain, though you could include those if you like. And then we have our stimulus. So, what do you think is actually going to happen when we simulate this? I'll give you a hint. I'm asking specifically about what happens when we put a 0 delay input into the inverter. We just go, it's 0 to 1 automatically as our voltage source.
Step function.
Well, that's the input. I'm talking about what's going to happen on the output. Think back. Okay, let me give you a second hint, because you know enough to solve this. But it's, so you think about your RC delay, right? We did all these RC delay models of all these circuits to try to test these transient delays and contamination delays, right? So what does all that mean? All these delays, a result of capacitances, and why do we figure out all of those delays in the first place? other than to solve the question so I can get my degree.
Avoid race conditions.
So avoid race conditions, but also to know how long it'll take us to have something go through a circuit, right? So we also know about switching, right? We also know that you have to be able to have a certain amount of time in order to create the channel in the PMOS and NMOS transistor, right? So what's happening is you're going to have this time, if you recall, where the channel in the PMOS is closing and the channel in the NMOS is opening. So if you don't allow sufficient time for that to happen, what's going to occur?
Wrong input, so you get wrong output.
Yeah, you're gonna get some of these little spikes, right? So it's not going to transition properly. So here, this is what's actually happening. We haven't properly accounted for it, so we just went straight from 0 to 1. My transistor went, holy crap. And then went back, went peak here, and then again, it doesn't quite work because it's getting overloaded, right? So what's going to happen is that's why you want to have some sort of rise time, and you can and that's why we actually calculated those rise and fall times in section 6. I'm sorry, in section 5. That allows you to. What's going to actually happen is if you remember from my dissertation, that one where I showed you that it had the rise and the other one followed very closely. When it follows very closely, you're actually dissipating less energy into the outside environment. So you want that to happen. This is heat. That's bad, right? This is heat. That's an example of when you feel the bottom of your laptop and it's getting really hot. This is the source of it right here. You're seeing you're running the computer too fast and it's not being able to switch it. At that quantum level, you're not creating the channel properly. You have two channels open and you get these power spikes. I promise all the stuff that I've been teaching in the course, is useful and not just do this problem. The end. All right. So, so it is. Let's stop here for this. So basically, I want to talk because it's noon. So I want to talk. I haven't had the opportunity to look over your essays. I still haven't received 2 of them. So if your group is here and you haven't emailed me your essay, do that. I think basically I'm going to email the SemiWiki guy, Daniel Nettie, today and say, hey, the essays are done. And I'll look over them and give them your edits. And then probably what's going to happen is you guys are going to post them tomorrow on there. And kind of keep an eye on them, respond if anybody responds, but I want you to focus on your exam. For those of you who kind of came in, the way it's going to work, your groups are going to do, the TGOs are going to be the opening portion of your lab reports. You're going to have 3 lab reports. You're going to think of it more as, don't think of it as much as like coding assignments as much as, remember, the lab instruction to go through, you follow certain steps and then something happens. That's what's going to happen. This is more focusing on the tools. If you guys up to this point have done a lot of work in learning, you started out all the way at dopants, and then we started putting these together to create an inverter. You learned about how they're actually fabricated. You learned about putting together for AND gates. We learned about RC delay models. We learned about logical effort. Learned about if I have a certain number of gates, I can put them together, and based on that, I can figure it to try to optimize load capacitance in order to drive a circuit. Then we started learning about ratioed logic. What happens when I do have these trade-offs between power consumption and size? Particularly because PMOS transistors, they start to get really big. If you look. In this next example, we do the span out of 4. You see this load on load is 512 over 256. So that can get pretty big pretty fast. Then we started talking about what we have. I think we had the Titanium 2 processor. We had some sort of, we had flip-flops, and we learned about pulsed logic and we learned about these, we basically went through these steps of design. We started out with a transmission gate, with a pass transistor, and we went to a transmission gate, and we learned about the pros and cons of all of that. And go all the way up to where you had a buffered input, and then the loop on the output to stop these issues. You learned, you saw a circuit, you were able to present how that worked. And now we're getting into simulation and spikes and things like that. So basically, you guys have covered a lot of material. I believe you've covered all but 4 of the 15 book chapters already. The other ones are, I'm trying to figure out precisely how I want to phrase the rest of the course for in lecture to go with the labs, because a lot of stuff is like adders, data paths, memory elements, which you guys have should have learned already. And I'll probably go over, like, as the lab is going, if you have to design a memory element, we'll do that in class, and then when you do the lab, you'll have this as a reference. The whole goal is when you type this up, you type up the TGOs, and then when you do the lab, it should go, oh, okay, we've learned everything that we need to complete the lab. So, does anybody have any questions on what we've done so far, what you're expecting for the exam, expectations for the rest of the course, any comments like we have a big exam coming up on blah, blah, and I should know about it so that way I don't double book you or...
Okay, at the top of the article, we put UM student blog, and you said dash and then article name. Do you want us to put the article we referenced, or like come up with a name for our article?
Come up with a name for your article.
Gotcha. And then cite the original article.
Cite the original article at the bottom.
Gotcha.
And a number of you cited other ones. So say this was our original article, and we have also cited these for those of you who did that. Any other questions? Or just like, hey, we get to get out 11 minutes early today. All right. I did post the video from last lecture on there, so you have that as a reference for your exam. All right. In that case, if you guys don't have anything else, you're dismissed. The exam will be on available at Blackboard at 12:30. I've set it to come available at that time.